designing our own capacitors or something like that. So it's nothing that we're really going to probably end up using, but it is something that we should be aware of so I understand the physical characteristics of a capacitor. Then the coding, that's good to know, kind of get yourself in the habit of how to mark the value of different mylar capacitors or the ceramic ones, the round ones. And then this is where this comes into a little bit more of a play where we're going to be looking at. So we have capacitors in series. So our first thing that we want to do is we're going to look and be able to calculate out what our total capacitance of a circuit is. Again, just like resistors, if we don't have one particular value, we can either add our resistors in parallel or we can add them in series and get the value that we want in resistance. But we can do the same thing with capacitor values. Okay, we can combine or add or depending on what capacitance that we actually want. So the first one we're going to take a look at is capacitors. So when we're adding the total capacitance, and don't get confused between this isn't resistance. We haven't talked about the resistance of the capacitor yet. This is actually the physical size or the size of the capacitor. How much charge can it actually retain? So we want to know what is the total capacitance of this circuit. Well, when we're adding capacitors in series, it's like adding resistors in parallel. So for example, if I want to solve for CT, my total capacitance of this circuit is going to be 1 over C1 plus 1 over C2 and so on. So using your calculator, add up those three capacitors like resistors are in parallel, and calculate out what you get for our total capacitance. Don't just tell me what the total capacitance is. What does that equal? What does the circuit equal for total capacitance?
So you did the 1 over thing, right?
Yep, that's the formula that you want to use.
Oh, I see 4.5. Actually, I just did the formula up there, but it's 4.5.
Nope, man, nope.
1.0645.
Oh, maybe I get it wrong.
I got 1.5 micro.
I did.
That's what I got 1.5 micros.
You get that though.
So I got
You got to invert your
1.5
number.
microfarads.
So if you want to...
Yep. Well, I did.
Yeah, I did.
Okay, so take C1, do the inverse. So make sure you take the inverse of C1 plus the inverse of C2, hit your equal sign, and then do the inverse.
Yeah, I just did something.
Yeah. And just remember, just like resistors in parallel, remember our total is going to have to be smaller than what? The smallest capacitor. Since these are like resistors in parallel, our number should always be smaller than our smallest capacitor. Alright, so that's how you solve for total capacitance in a series circuit. Now, what we can actually use it, since we have, what type of circuit do we have here? So what's another name for a series circuit? Okay, so we can use these capacitors as actually voltage dividers. So how this actually is going to end up working is that this voltage supply, this is a DC power supply. I'm going to go ahead and turn my power supply on, and what's going to happen the first instant I turn my switch on is that all these three capacitors are going to act like a short. So that's something, you should write that down. The nice to know thing is that when I first turn on power, my capacitor is always going to act like a short. And then after a given certain amount of time, my capacitor is going to act like an open. So when I first apply power, my capacitor acts like a short. And then as I hold that voltage DC on there, all these capacitors are going to act like an open. And once they act like an open, they're all going to have a certain amount of voltage drop. So what's going to happen is when I first apply my voltage to this thing, all these capacitors are going to act like a short. And so my current is going to start to flow. And this current is going to start to flow, and it's going to start charging up these capacitors. And which one do you think is going to charge up first? The smallest one. So this 3 microfarad one is going to charge up, and then once that one charges up, it's going to act like an open. Once that capacitor acts like an open, then my current is no longer going to be flowing through there anymore. So what happens is that C1 completely charges up to its fullest potential, and then C2 is not going to be fully charged, but it's going to be pretty close, and then C3 has still a long ways to go before that one's fully charged. So these two here never actually end up ever really fully charging up to it. So C1 is going to actually end up charging up all to its maximum potential, and that one's going to drop the largest amount of voltage. And then C2 is going to drop the amount of voltage, and then C3 is going to drop the amount of voltage. So to calculate out your voltage drops across your 3 capacitors, you can use the formula that's on the bottom of page 403. So basically it's just our voltage divider formula. So our voltage of our certain capacitor is equal to my, now it's just kind of a little bit inverse from what we used on our other formula for our voltage divider formula. Here we're going CT over your whatever capacitor number that you're looking at.
Sure.
Yep.
Is that actually come on to your number? So,
Huh?
that's
Multiplied by my voltage source. So we're going to take our total capacitance divided by our 3 microfarads, multiplied by 100 volts, and what do you get for a voltage drop across C1?
50 volts.
50 volts? Okay, so then what do you get for a voltage across C2? 30 volts. And then your voltage across 20 volts. And since I have a series circuit, if I add up all those voltages, do I equal to my source voltage?
Yes.
Okay. So it's just like we said, C1 fully charged up, got the most amount of voltage. C2 didn't get to charge up all the way, and so it only dropped to 30 volts, and then C3 ended up dropping 20 volts. Okay? Because this capacitor is twice as large, almost over twice as large as this one. It didn't drop as much because it didn't get to fully charge up to its fullest potential. Okay? Any questions on that one? Pretty straightforward. All right. All right, so then let's take a look at capacitors in parallel.
That fourth one, and the voltage total you can see. The fourth one, 934.
Oh, yeah, there, yep.
The voltage total you can see.
Yep.
Gives you the voltage of C3.
Yeah, let's see here.
It gives you a voltage on that.
Right. So you have so you have your voltage here.
Yep.
Let's see how we can figure out your V total.
Funny resource and
how are you going to get your V total?
Well, you got C.
Get your C total, right. Yeah, so you get your C total, so your C total would be what did you get for your C total?
Got the inverse.
Since we know that it's all proportional, we know that, let's see, I gotta think about how to solve this one. That,
It would be VC2 is equal to 20 volts is equal to CT over C2, and then you just remove C1, C2 on the other side of the equal sign, and it gets you
right, yeah. So yeah, because that's what you would need to,
plug in your numbers and then flip it
plug in
around.
your numbers, yep. So we know that we want DSP
by itself.
by itself. So what we want to do is take whatever we do here,
Flip it over there.
put it over here. So then this one would have to all be,
CN over CT.
it would have to be CT over
Yeah.
CN, right?
Or you multiply both sides by CN over CT.
Multiply, yep. Okay, so I guess I'm not mad. All right, so let's see. So this one was our voltage of our unknown. Okay, so you're saying you do what now, Bob?
Well, multiply both sides by CN over CT.
So CN
Right,
over
yeah,
CT
exactly.
is the reciprocal
Yeah.
of CT over
So
CT.
that would be VS by itself is equal to...
So VCN times CN over CT.
Exactly, yeah.
Wait, okay, say it one more time. I was trying to listen to both of you at the same time.
The CN over CT is the reciprocal of CT over CN, so they'll cancel each other out. So you want to take CN over CT on the other side of the equal sign. So you want to times it by that.
So I want to multiply it
So
by...
it'll be CN over CT times VCN
Yes.
Yep.
okay.
Equals VS.
will equal the voltage.
Then that would equal, then this would count.
Yep.
Get rid of that, and that would be... All right, there you go.
And you got that information there.
Yep. Yep, so... Yeah, and I get... I'm kind of, a lot of times I can't, to be honest, I don't remember doing all these little... But what I do a lot of times, if I'm out in the field and I get on these, and I know that this is all proportional, I know that... So, C3 would have to be, if this one's 50 microfarads, and it's at 20 volts, and we know that this one's going to drop more voltage than this one,
4 times as much.
so I know that this one's going to have to be 4 times smaller than what this one is. So C3 would equal how many volts?
5 volts.
5 volts. Okay, so now I know that. So I know that this is going to be 5 volts. This one I know is going to be. It's going to be larger by the ratio of 20 volts, and then I would get that voltage and I'd add them up. Because I'm not on the fly and in my head. I couldn't do this in my head if I'm off the field. And so I ration here. I'm very a rational person. I just kind of,
Rationalize that.
yeah, I rationalize it all in my head.
Not when that 49 converts.
I've been under pressure way too many times, and so that's when I quit do this. I can do this in my head, but I can't do this in my head. But yeah, so we always have those guys that, some of you guys that are in math and stuff, and I just had this. Yeah, that's, I gotta remember, I should go back and try to remember and know how to do all that stuff again, but I kind of rationalize everything out.
C1 would be how much bigger than
C1 would be what would be,
It's easier to go from C1 to C1 because those
freaking overs that measurement?
Yeah, it'd be 5.
yeah, because you could do that because you know that this one's gonna be, what, 5 times, this is gonna be 5 times larger, right?
Yep.
That's there. I like that. See, he's catching on. Yeah, so this is going to be, so this voltage across C1 then is going to be what?
25 volts.
25 volts. So now we know that this is 25 volts. Then I got 25, 20, so that's 45 plus another 5 volts. So that means that my DT is equal to what?
50 volts.
50 volts. Yeah. Yeah. So I kind of rationalize everything out when I get under pressure.
Yes.
Glad you asked that one. That was good. That was a good question. I kind of had to think about that one.
Math complete.
All right.
I follow that too.
That all make sense then, Josh? Yep. So here's the formula that Jesse and Bob gave you.
Yeah, that seems
That would work.
Yeah.
But this one here, if you're trying to, if you can't remember how to convert things when you're out in the field, and just kind of rationalize everything out. If I know this here, and I know this is 4 times larger, then you can just do it. I just kind of rationalize everything out. So for example, like, I know that this one is going to drop a certain amount of more voltage than that one. So if I take so what I would have done, they did it here, which was even more logical than what I did, but I would have known that this one's going to drop a little bit more than this one is, so I would have taken my 50 divided by my 40, get a relationship, and then I would multiply my, so I would have got, so if I take 50 divided by my 40, I get 1.25. That's my relationship between those two, my ratios. Then I just multiply it by 20 and I get 25 volts. Yeah.
Anyway.
But you guys made it difficult on me. All of a sudden you guys started talking about how you can convert. You guys aren't supposed to say that crap. I got to be a little quicker on how I solved it, but I had to.
It's just like
had to think through it.
algebraic formula.
I know you guys do it all. You're doing it all the time. Yeah, it makes sense, but when but it's been a while. It's even been a while since I've done a math class. I rationalize everything out. Yeah. All right, Josh, you're on my list. Yeah. Let's see today. Ooh, let's see what's. All right. So then, since we understood so then we understood the first part, then I kind of skipped over the parallel circuits. I kind of went right into a series parallel, since we kind of understand how everything works. So then we're going to kind of jump right into it. We're going to kind of do the combination of both the series and a parallel capacitors together. All right. So again, just like we did when we were in series parallel circuits, you want to reduce it down to one equivalent capacitor. We're trying to find the CT of our capacitor there. So for example, here we know that drop off. So what two capacitors can we combine first? What do you want to do?
Yes.
Yeah, C2 and C3. We got to combine these two, and we want to get this down to one resistor. Oh, Jesus, gosh. You guys got me all worked up.
He's stuck on DC.
You guys got me all worked up over not doing my algebraic version anymore.
Well, that's a fine looking capacitor.
Yeah.
It's a new breed.
Are we missing something?
All right, so then so this is our C1. This is going to be a combination of C2 and C3. And then this will be C4. This is all the farther we need to really go down to, because now once we get it down into a series circuit, then we can just go ahead and all three of them as resistors are in parallel and add up our total. So we really only need to get down to one. Once we get down to a series circuit, then we can kind of stop at that. Then we can just do their voltage divider formula and all that. So our first step is that we want to combine C2 and C3 together. So now when we're working with capacitors in parallel, it's like adding resistors in series. So we can just add those two together. So we just take C2 plus C3, and we'll end up getting what?
2 microfarads.
2 microfarads. C1 was 2 microfarads. And C4 was 1 microfarad. All right. So now once we have that, then we can go ahead and add up our 3 capacitors like resistors are in parallel. So now what do I get for total of capacitance for this circuit? And we know that it has to be smaller than what?
1 microfarad.
1 microfarad. So what do I get for total capacitance?
500 picofarads.
500 picofarads? Everyone agree with that? Anyone else get that?
I haven't gotten that far.
Okay, so you should get 500 picofarads. So now we want to solve up for our voltages. So again, we can just use our voltage divider formula. Using this one, we can just figure out what our voltage drops across each one. And which one's going to drop the most amount of voltage?
C4.
C4, that one's going to drop our large amount of voltage. So we should be double checking our work as we go through it.
So 100 nano? Yeah, you're smiling.
So on these parallel capacitors, you just add them like series?
Yep, just add them like in series. Yep, we won't talk about it.
Series, yeah, like parallel.
Yep. Yep. It's all in the book too. I mean, it's just in there. It's just adding. Yep, and I'll show you why.
Oh, my bad. Yeah, he's right. It's nano.
Oh, and then I was just.
Yeah,
I was gonna say it was like a little bit too small. So it should be 500 nanofarads. That was a little small for that. All right, so what do we get for voltage across C1 then? What'd you get?
For C1?
Yep.
Oh, that was 12.5.
12.5. 5.
I was thinking for the other two. No, wait.
You're right. You're right.
No, the C4 should be 12.5 because that's the smaller one. The C1 is going
So this one should be 12.5. Then C2 and 3 should be half that, right? So that should be 6 and a
to be
quarter.
And then since that one's the same as the other,
This one should be 6.25. Yeah, so a lot of times, once you get to 1, then you can just kind of, again, just rationalize it out, figure out what it is. So the 1 microfarad is going to drop twice as much voltage as the 2 microfarad ones do. So the C1 is going to drop 6.25, C2 and 3 are going to drop 6.25, and then C4 is going to drop 12.5 volts. So what's going on with this circuit now is in that, again, so my capacitors are all going to act like what when I first turn on my power? Short. So all my current is going to come down, it's going to go through this first capacitor. Then I'm going to hit my current node, and some of my current's going to go this way, and some of my current's going to go this way. And then those two currents are going to combine, and then they're going to go across C1 and then back into my power supply. Then, what's going to happen is that C1 is going to charge up, and then that one's going to act like a what?
Open.
As an open. So that one's going to act like an open, and then those currents is all going to stop going across these. And so the C4 is going to charge up to its fullest, and then C2 and C3 aren't going to charge up to their fullest because it's a combination of the 2 microfarads. But since they're in parallel, what remains constant in a parallel circuit? Voltage. So both of those are going to, since my voltage is going to remain constant across the parallel circuit, both of those are going to drop their 6.25 volts going across each one. Even though I have two separate size caps in there, my capacitors are still going to charge up. They're both going to charge up to the same amount of voltage because of the parallel circuit. And then C2 then is not going to, the current's going to stop before that one charges up, and then that one's also going to drop its 6.25 volts. Okay? But a lot of our rules still hold the same. Parallel circuits, voltage remains constant in parallel circuits. My current remains constant through a series circuit. So all those rules still apply. The only difference now is that when I first turn on my power, my capacitor is going to act like a short, and then when I keep my source on there, then it's going to act like an open, and then all my current's going to stop flowing. And the one that the smallest capacitor is always going to open up first and stop the current. So the total capacitance of this circuit here then is actually increased. So let's take a quick look at that here. So if I break that circuit down, that parallel circuit down a little bit, and I just break it down to the parallel circuit. So if I just put on any old source on this thing, let's say I put in 10 volts on here, what's going to actually happen is that that current's going to start to flow. The current's going to start coming out of our power source. It's going to go into our first current node. Some of this current's going to flow through here, and the remainder is going to come up and flow through here. Now, as that current starts to flow, which one is going to charge up first?
Smallest, 0.5.
The smallest one. So this one's going to charge up, and it's going to charge up to its 10 volts. And then that current through this branch is going to stop. So now I don't have any current going through here, but since I have a parallel circuit, what happens with this one? Does this one stop charging?
Nope.
Nope. That one keeps charging. And what it's going to do is it's going to go up until it reaches the source voltage. And that one's going to charge up to 10 volts. And then that current is going to stop. But when I first close that switch, they both act like a short. Since I have a parallel circuit, some of that current's going to flow this way, some of it's going to flow this way. This is going to charge up to its maximum amount of voltage that the source is, then stop. And this one's going to continue on until it gets to the maximum amount of voltage, and then it's going to stop, and then that current is going to both stop. And then those currents, while they're charging up, are going to go both going back that way. So it's the same thing here, even though I have a series parallel circuit. This one, they're going to start to charge. They're going to charge up at the same rate. This one didn't charge up to its fullest potential, but it's still, because of the parallel circuit, it's going to charge up to the same voltage as C2 is. Okay? Again, these are good to know. You probably aren't going to be using them as series parallel circuits. The big thing is knowing that if I needed a 2 microfarad, I could put 2 capacitors in parallel and get my 2 microfarad. If I need something smaller than a 1 microfarad, I could put two of them in series, and then I would get 500 nanofarads if I put 2 1 microfarads in series. Right? So I can do my combination of any capacitors that I want to get the value that I would need for my capacitors. And it doesn't matter, my circuit, my source, when it's looking at this circuit, well, this would be a good one. My source here doesn't know if there's 4 capacitors at all these different values, or if it's just one value of 500 nanofarads. All it sees is that it's a total capacitance of 500 nanofarads. So whether it's 4 of them all together or just one that size, the circuit still will react the same way no matter what. All right. So any questions on that? So it's just more looking at, how does it charge, how they discharge, which ones are going to charge up first, how does the voltage across them are affected and stuff by it. All right. So those are voltage going across our capacitors, both in series and in our parallel and then series parallel. All right, so we'll try it. so let's look at, so when we were doing it with this circuit here, the minute I turned on that power, these things almost charged instantaneously. There was no, other than a little bit of the resistance that was in the wire and stuff, the minute I turned on that power, they did act like a short, but almost an instant after that, they were already up to their maximum amount of voltage. Those capacitors are going to charge up because remember, our electrons are flowing at almost the rate of light of speed, and those things charged up pretty quick. So there's another condition that we use when we're looking at capacitors. And we're going to look at capacitors in DC. So on page 407. So when we first turn on, so again, when we first turn on our power supply or we close the switch, what's going to happen is that current's going to start to flow. And it's going to start separating all the electrons and the protons on each side of that, on that capacitor. And then that capacitor is going to be fully charged. All the electrons are on one side, all the protons are on the other side, and it becomes fully charged. Once I open up that switch, then that capacitor is going to maintain that charge until I go ahead and discharge it. The only way I can discharge it is if I give it another current path. So let's take a look at it. So here now we end up putting in a. So here's my. Now I have a resistor and a capacitor. And then a resistor. What's the definition of resistance?
Opposition to current.
Opposition to current. So what's going to happen is that's going to slow the rate of my current going through that capacitor. It's going to take a certain amount of time now to charge up that capacitor with that resistor in there. So what's going to happen is I'm going to close that switch and that current is going to start to flow. It's going to charge up that capacitor. That capacitor is going to fully charge up to the voltage. So when I first close that switch, the capacitor acts like a short. And the voltage I measure across the short is my 0 volts. So I'm going to get 0 volts across my capacitor. All the other remaining voltage then is going to drop across that resistor. So whatever my source voltage is, R1 is going to drop that voltage. Then that capacitor in my current is going to be at, it's also going to be at its maximum because I have less resistance than that. I only have that one resistor. That capacitor is going to act like a short, so my current is going to be at the maximum. The voltage across my capacitor is going to be at 0 volts. Then as I keep that source on my capacitor, eventually that capacitor is going to charge up. It's going to act like an open. And I measure my source voltage across my open. So that's what I'm going to be seeing across my capacitor. I'm going to be measuring my source voltage. The voltage across R1 is going to be at 0 now because I don't have any current going through there. And my voltage across R1 is going to be at 0 volts, and I have no current going through there. Now that capacitor has been fully charged up. Then what's going to happen then is I'm going to replace my power supply. I can put a jumper in there or put a short in there or put a switch in there. I'm going to get rid of my source. Now what happens is that I got an electrical path now for this capacitor to discharge across that resistor. So before the current was flowing through here, I charged up that capacitor. My polarity was negative, positive. It was going through my resistor, negative, positive, and then back in. Now I go ahead and I remove my source and I put in a switch in there, and now my current reverses direction. Now my current's coming out of my capacitor, now it becomes a source, comes out of my capacitor, through my switch, and then across my resistor with a negative positive, and then back into my source. So you can see that the polarity across my resistor has just changed. Before it was negative positive, now it's going to be negative positive. Because now now my source now becomes my capacitor, and then that's going to start to discharge across that resistor. And depending on the size of that resistor, it's going to be how fast it discharges across that resistor and how long that goes. So then that voltage across that capacitor is going to start off fully charged, and then it's going to slowly go down. As that voltage across my capacitor starts to go down, so does my current, and my current is going to end up being 0. So when I first close this switch, so if let's say I had 10 volts here, I charged up my capacitor up to 10 volts, I close that switch, now I discharge my voltage across that resistor. That resistor is going to see its maximum amount of voltage of 10 volts and then slowly decrease until my capacitor discharges completely 0. Then the voltage across my capacitor is going to be 0, and then the voltage across my resistor is going to be at 0, and then I'm not going to have any more current going through there. Okay? So that's going to be so that's kind of our charging and our discharging of our capacitor. Then there's a direct relationship to how fast you charge up these capacitors with based off of what we call our RC time constant. I'm not sure where to get to it. Let's get that on. Start breaking that. Quite get into that. Yeah, we'll probably have to finish on for this tomorrow, but make sure that what we'll do is we'll quit here, because if we get into RC time constants, that's going to be we're going to be going well over our time here. I don't want to get into that halfway into that. But go over that stuff. Make sure you read the stuff here tonight, so that. So we're going to start going over 409. On page 409 is where we're going to start, but I would go ahead and read over that whole chapter and take a look at that. I'm really kind of going through it pretty quick here.